While Bayes' law is a profound and fundamental theorem in probability, the law itself is very simple. Why? Because it derived in a very simple way from the law of conditional probability. Let's recap. The probability of H giving E, or P of H giving E, equals to the probability of the intersection of H and E divided by the probability of E. But the probability of the intersection of H and E exactly equals, by definition, to the probability of the intersection of E and H. What does it matter if I want both A and B to occur at the same time, or both B and A to occur at the same time? It is the same thing. Therefore, we can do a simple math trick that says the following. P of H giving E equals P of the intersection H and E divided by P of E. And P of E given H equals to the probability of the intersection E and H divided by P of H. And since the probability of the intersection of H and E equals to the probability of the intersection E and H, we can write the following equation. The probability of H given E equals to the probability of E given H times the probability of H divided by the probability of E. That is, ladies and gentlemen, the legendary Bayes' theorem. Again, it comes in a relatively simple manner from the definition of conditional probability. But the most powerful part of Bayes' theorem is the philosophical understanding that it gives us. P of H given E is in fact the posterior probability. What is a posterior? It means after the experience. Or in our case, it is a probability of H after we have seen the evidence E. What is P of H? P of H is a prior probability. Those who are familiar with philosophy will recognize a priori and a posteriori sentence. An a priori sentence is a sentence whose existence or correctness doesn't rely on past experience. P of H meaning the prior probability before I got the evidence. P of E given H is called the likelihood. The distinction between probability and likelihood is fundamentally important. Probability attaches to the possible results, while likelihood attaches to the hypothesis. We will dive deeper to this distinction later on in this chapter. One thing it is very important to understand that P of H given E should be different than P of H. Why? Because the evidence is supposed to provide us with some information regarding H. If P of H given E equals P of H, then what I'm saying is there is no relationship between the evidence and the hypothesis. And if there is no relationship, the evidence cannot provide any information regarding the hypothesis. We can think about it in the following way. What are the chances that the next person walking in the door will be male? Approximately 50%. But what are the chances that the next person to come through the door will be male, considering that they have a J letter in the name? Probably still 50%. The evidence doesn't provide us with anything about the hypothesis. But what is the probability that the next person that comes in the room is male if we know their height is 2 meters? This is a different story, since height is distributed differently between males and females. In the next video, we will show the most canonical example in all the topic of Bayes' theorem, because it explains just how much sometimes our intuitive understanding of probability is wrong.